Illustrating how back EMF works. When we power this circuit, the electrons in the current create a magnetic field around the wire as they move through it, as shown by these blue arrows. If the wire is formed into a coil, like this inductor, the magnetic field lines converge in the center. They gradually build up to a maximum magnetic field that is much stronger than the one around the straight length of the wire. Let's watch this again, but this time we'll pay closer attention to what's happening in the wire conductor. In this parallel circuit, the current can travel either through the inductor or through the light bulb. When the current reaches this junction, it splits and flows to both the inductor and to the light bulb. The magnetic field around the inductor reaches its maximum field, the back EMF fades, and the current now favors the path through the inductor because the bulb creates some resistance to the current. The same phenomenon occurs when the magnetic field is shrinking, which happens when we open the switch and stop current flow from the battery. Once again, the back EMF opposes the change that created it. In this case, the change is the cessation of current. So, opposing this change, the back EMF wants to maintain the current, which flows once again to the bulb, causing it to flash before it fades away altogether.
Electrical charges generate a field around them. These fields of force repel and attract other electrically charged particles. Like charges repel, and opposite charges attract. When enough of these charged particles are separated, a potential difference is created. Electromotive force is a potential difference measured in volts. The symbols commonly used for electromotive force are E or V. The potential difference in charges is what forces electric current to flow. There are 7 fundamental forms of electricity generation. All of these forms of electricity generation create an electromotive force, or EMF. One of the most commonly used forms of electricity generation is the electrochemical reaction, or better known as a battery. The potential difference across 2 open terminals is known as the unloaded voltage. The electrical potential difference forces current flow when a circuit is attached to the source of EMF. There is typically some amount of resistance in all electrical components and devices. When current flows, the voltage across the terminals of the source of EMF is no longer the unloaded voltage value. There will be a voltage drop inside the device due to the internal resistance of the EMF source. The DC power supply is a commonly used device in the lab. This device has the ability to create different amounts of electromotive force. As the voltage is increased, the potential difference between the terminals is increased. Note that the unloaded voltage of the power supply is set to 5 volts. A DC power supply will experience a loss of potential difference due to the internal resistance of the supply. When the circuit is connected and current starts to flow, the internal resistance of the power supply reduces the applied circuit voltage to 4.7 volts. Electromotive force is the potential difference that forces current to flow in a circuit. We have looked at a couple of different sources of EMF and at some practical applications.